Alright, let's look at sampling distributions on our review here. First thing we're asked to find is know how to get a real sampling distribution. A real sampling distribution is if you were to go out and take lots of random samples of the same size from the same population and make a graph of all your means or all your proportions. For example, if our population here is Byron High School and I wanted to make a sampling distribution where sample sizes of 40, let's say. I would go and take a random sample of 40 and plot the average. Okay, so there's the average. I took another random sample of 40 and plotted my average. Another sample of 40, another sample of 40. Obviously, we would never do this in real life. We would spend our entire lives collecting more samples and people would probably stop responding to our surveys. However, in theory, if we were to go out and do this, what happens is we get some really unlucky ones that are very low and far away from the true mean, if the true mean is in the middle. We get some very lucky ones that are very much exactly the same. On average, we get more ones that tend towards the actual answer than ones that are far away, and it typically will end up creating a fairly normal shape. The larger the sample size is, the more normal this pattern will look. If you have a very small sample size, you don't necessarily get that, depending on what kind of question you're asking. But if you have a large sample size, it doesn't really matter what you're asking about, even if the population is skewed, because when you take all the averages, it ends up forming a fairly normal curve. That's a real sampling distribution, and that's how you would get it. Because of the fact that it's silly, because of the fact that it takes so much work to generate something like this, and if we were to go out and take thousands of samples of 40, it would actually be a lot easier to just take a census and just ask everyone and know the right answer. So that's why we would never do this in real life. The purpose of it is that we know from doing it a few times kind of in the lab that we get this pattern every time. And that pattern is super useful because now I can go out and fake it. I can go into StatKey and say, hey, my data looks like, my original population looks like this. Can you randomly simulate drawing from this and pretend that's a whole population and generate a sampling distribution? StatKey says, oh sure, whatever dude, there you go. Samples of size whatever, you will get something that looks fairly normal shaped out of that. It will come closer together. The averages are going to be close to the actual average, and the shape will come out fairly normal. That's the power of the central limit theorem. It says when you take samples of a larger and larger size, the spread of the sampling distribution, that standard deviation, goes down. We say we don't just have this, we have it divided by our square root of our sample size. Bigger sample sizes reduces the spread. That's very powerful. The other big thing that it does is it says, hey, I don't care if you started with a bimodal or a skewed distribution. If you take a large enough sample, I'm going to turn it into a normal curve for that sampling distribution. It's pretty magical. So StatKey does this just through random simulation. So we don't necessarily have to get a normal curve. It's just that we often do. When we jump down to the kinds of inference that we do, where we do a traditional confidence interval, we start with the assumption, hey, it's going to be a normal curve. I'm going to take whatever sample mean I got and I'm going to plop a normal curve on top of it because I know that sampling distributions typically look like that. We check our assumptions ahead of time to make sure that the conditions are right to make this work. For means, we say I have a large enough sample n is greater than 30. That pretty much will, in most situations, guarantee you a fairly normal shaped sampling distribution. Other things we check, we have a random SRS and we have population sizes large enough. That helps us make sure that, one, we have good data, and two, that we don't run into some weird probability issues. Getting back to our list, let's see what things we've checked off. We've talked about these first ones. We talked about the central limit theorem. I skipped this section. We're going to go back to that. Our three assumptions for means, we just talked about that, making sure that it's going to give us that normal curve that we expect. For proportions, we don't worry about the total sample size being 30. We worry about how many successes and failures. And the reason is because when you have a proportion, you have n's. You have 0 to 100% or 0 to 1. With means, there isn't necessarily a 0 all the time, because sometimes you can go negative numbers, whatever. But when you bunch up against these n's, let's say you have 1 out of 100 or something like that, your sampling distribution is going to be very skewed. Even though it's a large sample size, it will still end up skewed because it's bunched up against the edge like that. And those of you that have collected data and put it in stat key where you have this very small number of successes or small number of failures, you'll see that it bunches up against that edge and causes a skewed distribution. So when we're trying to make sure we have a normal curve, if we have enough successes and enough failures, at least 10 of each, we tend to get a more normal looking distribution. So that's why it's a little bit different for proportions. Last one on here says, understand that the standard error is just the standard deviation of the sampling distribution. When we talk about standard error, it shows up in the confidence interval formula, it shows up in the hypothesis test z-score formula. What we're talking about is if you take your original population and you take averages, take random samples and plot the averages, we say that this new curve gets a reduced standard deviation. It goes down. We call that standard deviation of that curve the standard error. This right here, the central limit theorem's thing that says sigma divided by square root of n is our new standard deviation, that is called standard error. So when you see standard error thrown around, it's talking about how spread out is that sampling distribution. For proportions, we have sampling distributions as well, and it has that really awful formula, the probability of success times the probability of failure divided by n. This thing right here is the spread, the standard deviation of the sampling distribution, called the standard error. So that's what standard error refers to. Last thing, going back here, it says, let's get back to that central limit theorem idea. Describe what the sampling distribution of means approximately looks like at different sample sizes. So if the starting distribution has a mean of 4.2, a standard deviation of 3.2, and is very bimodal, when you're taking samples of size 14, what will happen to it? Well, the mean never changes. The middle stays the middle. The standard deviation gets smaller. This right here, we say actually it's not going to stay 3.2, it's going to be 3.2 divided by the square root of our sample size. So it's going to get smaller, and that's exactly how it's going to get smaller. And the shape is very bimodal, so if we started out with something that looked like this, it's going to become more normal shaped with a size of 14. So maybe it'll look kind of like this. Usually 30 is kind of our magic number to say I can clean up some very non-normal distributions. But so 14 is kind of halfway there, so it'll clean it up a little bit. Next one says if the starting distribution is very skewed, has a mean of 120.2 and a standard deviation of 14.4, what will the sampling distribution look like? Samples of size 75. Well, if samples of size 75, we know that that curve is going to be perfectly normal. I don't care how skewed that original one is, it's going to become a nice clean normal curve at a sample size of 75. Mean doesn't change, so we just leave that. This 14.4, we know our standard deviation gets reduced. We take 14.4 divided by the square root of our sample size of 75, and so that will get smaller.